Hi, welcome to the 17th rule of acquisition. Ambiguity is for mystics. And in here we're going to do another disproof of the plane wave theory. This is in response to a comment on the introduction video to the new wave theory. And I don't know who David Zare is, but he's convinced that there does not need to be any wire or any charge construct for you to convert an electric field to a magnetic field according to Faraday's law. But we'll cover that when we get to that in the video. So, ambiguity in a model or theory indicates, this is my belief, okay? This isn't accepted by science, but I believe one day it will be. Indicates that the model or theory is a special case of a more fundamental explanation, meaning that somewhere along the line information is lost. And so we have a simplified example, a simplification of a more fundamental model, and there's information loss and there's ambiguity. Because when you have information loss, typically you have an ambiguity, and we'll explain what all that means. Let me give you the first example of Faraday's law. This ambiguity is for mystics. This rule of acquisition was the rule of acquisition that I came up with 20 years ago when I said there's something fundamentally wrong with Faraday's law and anything derived from it, which includes Maxwell's plane wave equation. So what you have here is you have a Faraday's law as it was originally written, and what it says is this represents a magnetic field going into the page. Those are like the arrows, the tails of an arrow, so that's a magnetic field going into the page. This is a loop of wire that's existing in the magnetic field, and according to Faraday's law, that if this magnetic field is changing and it's going down into the page, then what Faraday says is it's going to induce an EMF in the opposite direction. So if this magnetic field is increasing inward, okay, it's going to create a countermagnetic field, which is going to give you a current in the other direction, which would be this way around the loop. Okay, fine. This model here requires the construct of the loop for you to know, because the loop is what defines how much magnetic field is coupled and how much voltage. This is volts per coulomb. Okay? I'm sorry. This is joules per coulomb. That is the energy per charge that's induced in the ring. Fine, no problem. But let me show you where the ambiguity is. Suppose I put this ring here. Well, that means that the induced current at this point in space is going to be in this direction. If I put the ring here, it means that the current in the ring is going to be induced in this direction. If I put the ring here, then the charge induced is going to be in this direction. Well, and that's going to be in this direction. So in this case, that's what the electric field, according to Maxwell's equation, is going to be. So which is it? Which way is the electric field? Without the construct of the loop, you have no idea which way the electric field is going to go. And in Faraday's original writing, he's not saying that there's a vector field. He's saying that you're just going to, the energy coupled in the loop, in the direction around the loop, is what you're going to get. But Maxwell, when he corrupted this, he says, oh no, you're going to get a real vector electric field without anything there. So wait a minute. So you mean, if I have the loop here, and that's going to give me an electric field in the ring this way, and if I have the loop here, the electric field. So when I take away the electric field, how does a charge that's sitting right here, how does it know what to do? It doesn't know what to do. This is ambiguous without a closed loop. There is no meaning to this. This has meaning because the loop is part of this definition. But Maxwell threw away the loop, and now we have this ambiguous model that if you have a changing magnetic field and you have a charge sitting in it, you cannot tell which way that charge is going to go. There is no way you can get a vector field from an energy equation. An EMF is not a vector field model. This is. How can you go from having no vector on this side to having a vector over here? You can't do it. This is ambiguous. Without the loop, you don't know which way the electric field is going to be. So to sit here and say that, oh, well, yeah, this can happen without any intermedium of a charge, is ridiculous, because without the construct of the loop, you don't know which way the electric field goes. And if the loop is over here, the electric field at that point goes one way. If you have the loop over here, the electric field induced goes the opposite way. It's ambiguous. This makes sense because the loop is part of the construct. Let's go on to the next. We'll come back to this. Archimedes Principle is another example of a model that is ambiguous, because Archimedes Principle tells you that the force acting on a ship's hull is going to be proportional to the water, the weight of the water displaced. And the reason why Archimedes Principle is ambiguous is it doesn't tell you where the force is going to be applied. It just says there is going to be the amount of force. It doesn't tell you where it is. And because of that, it's ambiguous. And also, Archimedes Principle doesn't tell you about the effect known as squat. When this ship gets underway and it's getting speed, it's actually going to sink down into the water. That's called squat. So finding out where the force is actually applied and accounting for the phenomenon known as squat, you actually need more modern things called Pascal's pressure laws or models, along with Bernoulli's principle. Okay, and then you can derive this. This is a special case, a stationary case of these two here. This is a special case because it's ambiguous. And I have papers out that derive, well, we'll get to that, back to that. Addition and subtraction. And standard addition is associative. In other words, if I say A plus B is equal to B plus A, well, we say that's associative, but I'm telling you that's really ambiguous. Because in vector addition, the addition of vectors is not associative. For example, if I'm a ship at sea, and I want to go to where the treasure is, and my port is here, and my navigator says, well, you got to go west or east, X, and then go north, Y, to get to the treasure site. Well, if I say, hey, I'm going to go Y first because I believe that this is totally associative, well, I'm going to crash into the landmass before I even get out of the harbor. Okay, so and in vector addition, if you put your vertices into a graphics engine backwards, you're going to get shading on the wrong side of your polygon. So in vector addition, in vectors, except for the final outcome, the actual order is important for many, many, many different reasons. And a standard multiplication is commutative, meaning that if I multiply A times B, that's going to come out the same as B times A. That's ambiguous. Because in vector multiplication, and you can see my stuff on Q algebra, where A times B is not equal to B times A. There's a special case, though, where if A and B are parallel, then A times B equals B times A. Oh, and then over here for vector addition, if A and B are parallel, that's also the special case that allows A plus B to equal B plus A. You get the same answer. If they're in parallel, you're going to get to the same endpoints, the same path, regardless of which order you add them. And therefore, your path and your outcome is the same if they're parallel. Same with multiplication. If A and B are parallel, you're going to get the same answer for a vector multiplication, which works out to just A dot B is going to equal B dot A. Okay, so this shows that regular standard arithmetic is a subset. It's an ambiguous subset. It's a special case of vector algebra. And that's my opinion. That's not a scientifically accepted thing out there, but one day it will be. So ambiguity teaches us that we have a special case or simplification of a more fundamental model or theory in which information or degrees of freedom are lost. Such models and theories are valid under limited conditions. And applications of the simplified model or theory can be problematic if the limiting conditions are not known, because we don't know what the underlying fundamental model or theory is, and that's my explanation of Faraday's law, or Faraday's model. The problem with humanity is we all foolishly believe that everything we know is universal. So I know I'm going to expect nasty comments on this video, because there's still people out there that believe that humans have irrefutable knowledge of the universe. My friends, we are a bunch of retarded monkeys. We know very little. Ambiguity also tells us that a more fundamental model or theory exists. And that's what I call the ambiguity tell. Let me show you further ambiguity with Faraday's law. This is the one that actually really clinched me 20 years ago. The other one said, I got to look at it more closely. This is the one that set me off. If I take a lone charge that's accelerating, and that's my symbol for accelerating, a double arrow, it's going to create a changing magnetic field which is going to couple to the loop, and according to Faraday's law, it's going to properly induce an EMF in the loop. Okay? No problem. But what if I had a stationary charge sitting over here and I induced a current, a changing current in the loop? Well, Faraday's law does not give me an answer to this problem, nor Maxwell's version. It nobody does. And that says to me, if charges are the most fundamental building block of electromagnetic theory, and Faraday's law only gives me an answer one way but not the other, then something is wrong. Because this wire is basically a whole bunch of little charges that are accelerating when I put a DIDT in there. So you mean charges only when they're accelerating outside of a loop can induce a loop? An EMF in a loop? And a changing current in a loop does not induce force on a charge outside? There's something wrong. There's a lack of reciprocity here. And so therefore, that's why I went on the search and found the model called new induction. New induction basically says that the force on a target charge, whether one can be the target or the other one can be the source, if you take the acceleration of one charge and you take the distance between them, which is r from source to target, and multiply by the charges, the charge of the two charges, times km, which is mu over 4 pi, which is 1 times 10 to the minus 7, you'll be able to know the force acting on the target charge. Okay, and if you apply new induction and you derive this for mutually inducting loops, you get this equation, which looks remarkably, and this is for low frequency wire constructs where the wavelength in the wire is much longer than the length of the wire. I got this backwards. Okay. This looks remarkably like the Newman equation. The difference is the Newman equation has the constraint of closed path integrals. This is just an open or closed path integral. It doesn't matter. This has higher degrees of freedom than this does. This is applicable to dipoles. This is not, but people do it anyway. There's a lot of infractions on classical theory out there that people are just unaware of. And if you take new induction and you say that, well, this is Newton's model, F equals ma, but I like to use inertia for mass. It's inertia in kilograms. And the inertial force, if you're pushing on a ball, the ball's going to react to you. As the ball's accelerating this way, it's going to give you a force in the opposite direction to oppose your applied force. So the inertial force is minus the acceleration of the object, and that's what you're going to feel. And if we use new induction, and we put these forces together and divide both sides by negative a, we have inertia is km qs qt over r. Now, we said km is 1 times 10 to the minus 7, and we say that both the source and target charge are the basic elementary charge. And we say that the distance between them is the classical electron radius. Well, what we come up with is the inertia of this system of 2 point charges. These are not electrons. These are just inertialess point charges whose charge is equivalent to the fundamental charge. You get an inertia of these that's identical but have 1 degree more significant digits than the published mass of an electron. How wonderful is this? This is what Einstein was trying to do. He was trying to find the link between inertia and electromagnetism. Well, here it is. All we had to do was find the more fundamental expression of induction, and it's right there. Now you're saying, oh, this is remarkable. Why don't you go publish this in the journals? Well, I tried, my friends. Here we go. There's October 1997, astronomy, sorry, that's not the kind of stuff for us. Journal of Applied, examined your paper and conclude that it's not suitable for the Journal of Applied Physics, Science Magazine. Thank you for sending us your paper. We regret to say it's not the sort of work we publish. Really? A journal of science that does not publish science? Seriously now. And the journal Nature returned it without even doing the nice thing that the other journals did of putting a date stamp on it for me. All right, so And also in 2004, when I came up with new magnetism, I had sent all out to everybody too. Knowing it was going to be rejected, I just wanted the date stamp to show that I got the idea at the time I did, kind of a proof that I invented it kind of thing. And some people are saying, well, it's big money interests that are suppressing science. No, that gives humanity too much credit, people. What it is these journals do not want to publish something that shows that what they've been publishing in their rag journals for the past 150 years has been gibberish. Because if these journals have been publishing garbage for the past 150 years, what does it say about the peer review journal process? It means it's completely pointless. And they're all out of a job. They don't want to publish it because they don't want to lose credibility. And so they're going to just ignore me. That's all. But that doesn't matter. I'm coming for them. Don't worry. This stuff will eventually gain credibility, or somebody smarter than me is going to show me where I'm wrong. And so far that has not happened. Okay? I usually get letters like this from people that try to claim that I don't know anything about electric and magnetic fields, and they come up with this gibberish. They're just regurgitating stuff they learned in college. I mean, I don't know if this David Zare is a real physicist or engineer. It looks like he has some training, but it looks like he has no real application experience, because he's just regurgitating what comes out of a textbook, which you saw what I did to a textbook. So, no, that's reasonable men adapt to the world around them. Unreasonable men make the world adapt to them. The world is changed by unreasonable men. Thank you very much. The other thing that happened too is when I used new induction in 2007 for my graduate thesis, at the very end, when the dean found out what I was doing my paper on, the dean of the School of Engineering was a physicist. He had a conniption. And he had the power, according to the department chairs, to totally void my graduation and totally throw me out of the School of Engineering. Luckily, the department chair of this electrical engineering department, the department chair of the computer science department, really liked my work, and they basically told the dean that, listen, if you kick him out for ironically, Fairfield University is a Jesuit college that prides itself on critical thinking. And so what they're basically saying, you're throwing somebody out because he's doing critical thinking of what we all believe. And so they stood behind me. And it's funny because I read the book, The Fountainhead, after I graduated, and I'm like, wow. If you look at the opening scene in the book, Howard Rourke, who wanted to design buildings that didn't agree with what the public opinion of buildings should look like, he was basically thrown out of the School of Architecture or Engineering, whatever you call it, because he wanted to design buildings totally different from what he was told to build buildings like. And so it's funny that I am living this book. I know this is the movie. I got the book too, except I don't have the hot blonde to go with it. So anyway, thank you for your time. If you can please donate, I'd really appreciate it. I'm trying to, and if you want to get the word out, if I can get more traffic to the site and I can get enough viewer hits that I can do this full time, that would be great. Anyway, thank you.